There are patterns in NMR spectroscopy that are very common, and the more you practice this stuff, the easier it becomes. You start to see these patterns again and again, and very quickly when you're doing a pressurized exam situation and you're trying to work out the structure of something, if you know what an ethyl group looks like, you can see it. If you know what a T-butyl group is, you can see it, and it just speeds you up a lot. So these are the typical ones that are very obvious. These are the things that you should know from now in terms of what they look like, and be careful. The idea at the bottom is showing that is not an ethyl group, because why? The gap between here and the gap between here is quite different, right? The coupling constant is very different, so therefore they cannot be communicating. And that J value then tells you an awful lot. So the gaps between these lines here, this is the blow up, don't forget, is the same as the gap right there, if they are talking to each other. That becomes very useful. Now, we did talk about the use of J values. We talked about being able to analyze these signals and these spectra to a great degree, so you're absolutely happy with what's happening here. In pharmaceutical chemistry, this is very important to know exactly what the shape of the molecule is and where the protons are relative to each other. So use J values as you need to. This slide was trying to show you that taking this idea beyond situations in which you just have one type of neighboring proton is actually okay in this type of molecule. This is a freely rotating molecule. Okay, everything here is freely rotating, and the J values average out to about 7 Hertz between the protons on neighbors. So it turns out, even if you have protons that are different, and I would argue that the red hydrogens have green neighbors and blue neighbors which are different, N+1 still works in that simple type of system. I'll show you some examples today of more complex systems in which it doesn't work necessarily, but here you can see that will work. So N+1 on those simple acyclics will work, and you will get those typical patterns. So if you've got 4 neighbors, you'll see a quintet. If you've got 6 neighbors, you'll see a septet. The N+1 rule does work for that type of situation. Now, we started talking about this, and I'm going to mention this again because I've had some good questions over the last few days about this, and I want to make sure people understand it. For the most part, you will see N+1 and it will work to give you triplets and quartets and stuff like that. But occasionally you'll see details in which the molecule is locked. The rotation around there is locked. You can't rotate around a pi bond without breaking it. So that leads to some interesting situations in double bond and in cycles where you can't rotate. And this signal is for the hydrogen in the circle. And the idea now is, if you simply used N+1, you might say, okay, that red hydrogen has 2 neighbors, N+1 is 3, I expect to see a triplet. And that isn't a triplet. That isn't even a quartet. That is something different. And we'll call it a doublet of doublets. Okay, this will be a DD, doublet of doublets. And this can get as complicated as you want to, depending upon the type of molecule you're dealing with. Where it comes from is fairly simple. You have 2 different splittings. HA is splitting with the cis hydrogen and in a different sense with the trans hydrogen. Why doesn't it show up as N+1? Because the coupling constants are different. If the coupling constants were the same, maybe you'd see a triplet, but they're not, they're different. So in this example now, we'll see a doublet for this interaction, cis, and we say that's about 12 Hertz, and we'll see a doublet for this interaction, and that will be about 16 Hertz. So when we try to plot this, when we try to come up with a picture of what it should look like, this is a singlet. This is HA as if it had no neighbors. Singlet. And if HA had 1 neighbor, and that 1 neighbor happened to be the trans hydrogen, you'd see a doublet. Those 2 lines there represent the 2 lines of a doublet. So that's the first splitting. And we typically, on these types of pictures, put the largest splitting first and work our way down. Well, then we have a second splitting. So those 2 lines here get split again, both into doublets. So now we've got there, and we've got there, based on that 12 splitting between the cis-aligned protons, and that gives us this, what we call a doublet of doublets. So if you're confused, these 4 lines are now these 4 lines in the signal. That's where it comes from, and we can predict these things if we know what the molecule looks like. Or in the other direction, we can find out what the molecule looks like if we can work out how to use these spectra. Okay? You need to know those numbers. You know, it's on the line of something like pKa. If you know those numbers, 16 and 12, it will really help you get full points on a question when you're trying to work out a structure. Now, what I thought I'd do is bring in a couple of pictures. If you want to take a picture of this, go ahead. This is just FYI, but it's the type of stuff that we can do, and it's the type of stuff the honours students are doing for their projects this semester. We make a lot of this molecule. This is an azido sugar that we make a lot of to do various reactions with, and it's got a very interesting NMR spectrum. It is quite complicated compared to what you've seen, but you should be able to work out some patterns. Over here, this is a triplet. Over here, this looks like a triplet. That looks like a triplet. This looks like a doublet. These look like doublet of doublets, DD, and this is a doublet of doublets, a DDD. Now that's a fairly simple spectrum, and Dr. Jackson and I published something on this a couple of years ago in the Journal of Chemical Education for people to use in this sort of class, to try and see how this is useful but also limiting. NMR spectroscopy has developed over maybe 50, 60 years now to become extremely powerful with lots of different techniques to work out the structures of very complex molecules. So you're looking at that, you've just spent some time thinking about NMR, you're still new at this subject, but you might be able to have a go at that. Which proton on that molecule, there's only one proton, should be a doublet? This one at the top, this one over here, this one over here, this one over here, this one over here, or this one there? Which one should be a doublet? Which one should be the simplest signal? Let's look at this one. How many neighbors? No neighbors here, no neighbor over there, one neighbor here. So what shape? Doublet, right? And that J value between those two tells you its orientation. There's a lot of detail here you could go into if you take an NMR class in which the angles can be represented as J values. There's a definite correlation between the angles in terms of a Newman depiction and the actual J values in the signal. So that doublet is to start off. Now, without sort of going too far here, this is just to sort of whet the appetite if people are interested in this stuff in the future, certainly in a research sense. We do the experiments every day. I've now got a situation in which this proton and this proton, how are they aligned? Give me a Newman depiction, description of how they're aligned. Anti, and anti tends to give you the largest coupling constants. And what's the relationship between this proton at the bottom and this proton here? They're also anti, right? So they'll have a similar coupling constant. And you can find at the back, that proton up and this proton down, the relationship again is anti. Now, the problem with this spectrum is that it manifests itself as three triplets. And if they're all anti to each other, the coupling constants will be the same. So how on earth do you work out which is which? And for a carbohydrate like that, which is a biological molecule, you have to know exactly what you're working with. Now, we have defined some things in the past in terms of homotopic and antiotopic and diastereotopic. I want to finish this off by just looking at these signals down here because they're the most complicated and it'll answer your question. If you look at this system, I get rid of all that noise, this proton and this proton at the back are not the same as each other. It's a CH2 group, but if you ran that test with deuterium and you swapped out one of those hydrogens for D, and then you swapped out the other hydrogens for D, you get diastereomers. These protons are said to be diastereomeric. So therefore they're not showing at the same place. Okay, and those two protons are here. So this is an interesting concept in which, because they're different, they couple each other, even though they're on the same carbon. And because they have one neighbor down here, they will couple that. So if you couple two different protons twice, what shape do you expect? Doublet of doublets. Doublet of doublets. And there you do. You get two doublets of doublets right there. Okay, so it does show. Now, the best signal on this spectrum, as far as I'm concerned, is this one over here. And you could tell me pretty quickly, if you knew what you're doing here, that it's that proton at the back, because it has three different neighbors. It has an H neighbor over here, an H here, and an H here, all of which are unique and different. So you split it once into a doublet, you split it twice into a doublet of doublets, and you split it again into a doublet of doublets. Now, how many lines do you expect in a doublet of doublets? You got 2 in a doublet, you got 4, what do you expect? 8. Now you expand this, beautiful. You get 8 lines in that signal. And that's a DDD. That's as complicated as you'll see, and it's not anything I'll test you on, but these are the types of things we can do here quite easily using the instrumentation that we have. Now, in terms of using this in biology and using it in sort of structural biology to work out definite structures, we need some other techniques. How do we know the protons are up or the protons are down? How do you know the orientations of these things in the molecule? Well, we can use some other techniques. This is called nuclear Overhauser effect, NOE. And this is a through-space interaction. You can do this on the instruments in Ward Beecher over there. And you can see now that these protons, the red hydrogen there and the red hydrogen there, they're not neighbors. But because they're close to each other in space, they can influence each other in terms of their magnetic field. And this is a different technique to the one you've seen. This is a pulse technique that requires saturation of this one signal, and you see what else happens across the cycle. But very quickly, you can tell that these things are pointing in the same direction. And this is important for protein biochemistry and stuff like that. We can also do modeling, and we can also do crystallography over in Ward Beecher, and those are the types of things I'll talk about in the future. Now, the last slide there, the problem here is that we have 3 triplets. And if all the coupling constants are the same in those 3 triplets, you can't use the J values, because you can't tell which is which. So we do experiments like this. We do something called, in this case, it's called COSY, correlation spectroscopy. We have all these silly acronyms for these experiments, but a COSY experiment tells you which neighbor is which. And so you'll get this sort of mapping possibility, where if you can find H1, H1 is where was H1? The NH is over here. You can map that to H1, you can map that to H2, and you can actually spell out exactly which one those belong to. Some of you will end up doing this maybe in biology, if you go to graduate school in biology or biochemistry, and that's the sort of basis of that technique. So we've dealt with proton NMR spectroscopy apart from one thing, we've touched the surface and we've got some idea now what it's useful for. We now need to worry about some problems and how to use those problems to our benefit. If you spend time in Washington, D.C., like I did before I came here, it gets very, very humid. Arizona's dry, Washington's humid. Now, some molecules which contain things like alcohols or NH2 groups, I need to write that on here as well, any NH protons, those spectra can be problematic. If it's humid, they'll have an interference maybe with the IR spectrum. You'll see humidity, you'll see moisture in the IR spectrum. It also happens in the NMR, because these protons have an appreciable pKa. The pKa here is about 16. And what that means is it's weakly acidic, but it's acidic enough to do what we call exchange. And this idea is called exchangeability. If you identify a proton on your molecule, like a carboxylic acid or an alcohol or an amine, they can exchange with atmosphere. Okay, so if you ran a sample in Washington, D.C., where they built that place on a swamp, it's horrible, and it's very humid out there, you might not see this OH signal. But if you ran this spectrum in Arizona, where it's absolutely dry, you will see that signal. And all that's happening is that the proton is bouncing around between different molecules. You can imagine maybe some humidity in there is taking that proton off. And you've seen this before. H2O plus H2O gives you hydroxide and H3O plus, right? One of the very first things you learn in freshman chem. Doesn't happen a lot, doesn't happen to a great extent, but it does happen. So these protons are bouncing around, and in humid conditions, they might not be on that oxygen, they might be over here instead. So you tend not to see this sort of signal. Somewhere in between, maybe you take the spectrum here, and maybe you'll see a broad signal. So I want to draw your attention to this idea of a broad signal, BR. If you see a broad signal, typically it's an OH group or it's an NH group. And this answers the question, why on that chart is it such a broad range? Okay? The alcohol signals tend to be something like 2 to 6 or something like that. They're very, very unpredictable in terms of where they show. And it's all because of this exchange idea. They're not sat exactly on the same atom all the time. Whereas CH bonds, carbon-hydrogen bonds, which aren't acidic, they're stuck. They're on that atom all the time, and the NMR spectrometer can see them. So if you ran this under completely dry conditions, you would possibly see some splitting. And if it was in sort of, Arizona, I believe the symbol for Arizona is AZ. Is that correct? Yes. So if you're in Arizona, that will have a shape and this will have a shape. What will the blue hydrogen look like? What shape would it be? Because the proton on the oxygen will be there, and it will see it, and it will couple as a neighbor. So what shape should the blue hydrogen be under dry conditions? Doublet, absolutely, doublet. And you can even maybe see that this guy wants to be something, right? It's not quite, it's broad, but there's a little bit of definition to it. If it's completely dry and that proton is not exchanging, where might that be? What shape should that be? Triplet, exactly, a triplet, okay? And this is confusing and it's difficult, and this is why we have to be very careful setting up experiments to make sure that you've got the right conditions. So be aware of this. Now, this is something that isn't on the notes that you've got. You might take a picture of this when we get there. We can use this. We can use this to work out in a spectrum which is my alcohol proton or which is my NH proton. I might have a spectrum in which I have all sorts of signals. You can imagine in protein chemistry. I mean, protein chemistry is all about NH signals. How do I tell which of those signals in a very complicated spectrum, okay, which of those signals belong to the NH? Well, I can do a very simple experiment. I can add D2O, and we've seen a little bit of this stuff so far. It's a good solvent for organic samples because it's not going to be seen in the NMR spectrum. It's magnetically inactive, and so you can use it as a solvent to dissolve things up, and it won't swamp out your spectrum. But imagine now if you put this sample into some of this, and this is the solvent. You would exchange this for this. You would end up with a molecule which had D there instead of H. And because you've got a large excess of the D2O, all the molecules will have D there. Now that tells you which proton we're dealing with in the spectrum. Because guess what? Where this H will show up, if you put a D there, the signal disappears. So we do this all the time, trying to work out mechanisms, stuff like that. Maybe you want to see where the NH is, where the OH is, and stuff like that. You put a drop of D2O in your sample, shake it up, run the spectrum again. Some signals will disappear. And that tells you which ones they belong to. They were the acidic protons. So we can use that in a very useful way to do that. All right? Nothing hopefully too confusing there. Use this to identify that was your OH proton. The D will exchange and replace the H, and you'll end up with OD instead, and that will not show in the spectrum, so we'll see a disappearance. So there's a useful experiment. Now, I put this on because I'm thinking of ways to sort of make people enjoy this stuff and think about how it's useful. And there's an awful lot of pre-pharmacy people in here, and you might be wondering about, how do we tell about drug metabolism and stuff like that. Forensic science people too might be interested in this. All I'm doing here is a very simple experiment to put a deuterium on a carbon. And this is going to be useful to be able to trace, maybe, how the molecule breaks apart in some metabolic process, how it gets degraded in the liver, for example. I've started off with a very simple ethyl benzene. And I've run a series of experiments overall to get rid of one of those H's and replace it with a D. Now, you can't just do this with D2O. Those protons are not acidic enough. They won't exchange. But you can use acid-base chemistry in a very simple, very clever way here to be able to put a D on that one carbon. And what we need to do is activate it. And I'll say this now, and I'll say it at the end of this. If you can put a bromine on an atom, you can put a deuterium on that same atom. So you think about all the reactions we did to put bromine in a molecule, HBr with alcohols, Br2 with alkanes, stuff like that. Wherever you can put Br, you can swap it for a D. So you can put a D wherever you want, and that D does not show up in the NMR spectrum, so you can trace and track where that atom is. So here I put the Br on. Why does it go here and not here? Secondary, but even better than that, what? It's benzylic, right? And it's resonance stabilized if you put the radical right there. So that makes sense, and we put our bromine there. Now, in the lab, which you will do in the near future, and you hope it's not humid when you do this, you add some magnesium to that bromide and you get the Grignard. And the Grignard then is highly nucleophilic, but also highly what? Basic. It's incredibly basic, right? So you can use these things as bases. Now, in the lab, you want to avoid this. You want to run this on a day that's not humid, or you want to take care that the hoods aren't steaming up. There are no steam baths running next to your experiment, because that's kind of going to screw it up. You don't want this to happen, but you might want this to happen. Maybe you want this to happen. BOD is just deuterated water. And you can buy bottles of this stuff. You buy gallons of this stuff. And so what happens here is the Grignard acts as a base on purpose. We want this to happen. And if we swap the magnesium for the D, we end up with a deuterated version of the starter material. Okay? And there are people have started companies based on this idea. You can sell these types of things to pharmaceutical scientists who can then track and trace the isotopes throughout the metabolic process. Well, what effect will this have on the NMR spectrum? Think about the NMR spectrum of the starting compound. What do we expect to see for this signal? What shape should it be? It should be a triplet, absolutely. And what should the shape of this thing be? Quartet, because it's got 3 neighbors, right? What happens down here? How has it changed? What should the signal shape be for the CH3? Doublet, right, because the D is blank. You don't see the D. So it went to a doublet. What do you see for this one? Quartet. What happens to the integration for that signal compared to the starter material? It's smaller, right, because we started with 2 and we've now got 1. So we can do this with the ChemDraw. We can plot these things. There's the NMR spectrum plotted for the starter material. You can see the CH2 and the CH3. Which one is the CH2 group? Is it this one down here or this one up here? Downfield or upfield for the CH2 group? Downfield, it's benzylic. We should be on top of that now. So this is CH2, and that's CH3. And that makes sense for an ethyl group. So what we expect to see if we change this to the deuterated form is that this signal should get smaller, and not change its shape, because we still have 3 neighbors, and this signal will become what? A doublet, right? That's exactly what happens. So now we have a nice simple method for tracing atoms throughout a synthesis or throughout a metabolic process. Put a deuterium on there, see what happens to it. If the molecule blows apart in the liver and you end up with samples, where's the deuterium? Do a mass spectrum, do an NMR spectrum, see where it ended up. That's going to help you work out the mechanism of metabolism. Okay, moving on. We're pretty much done with proton spectra. We're done with the actual laying out the possibilities for what they look like. We now have to get good at using them. It's all about using them to help solve puzzles. So, typical questions. This is one I like a lot because it brings everything together. You have to know the chemistry to be able to draw the spectrum. If you don't know the chemistry, you don't know the product, you can't possibly draw the spectrum. So it tests whether you're on top of stuff. You're typically given in this picture, and this type of question, you're given a starter material, you're given some conditions, and at the end of that, there's nothing here. You have to give me those products. And at the bottom, you get a blank spectrum with the x-axis laid out, and you have to draw the spectrum. So it's quite tricky and quite different. It's fun if you know what you're doing. So in this case, we haven't really done, oh, yes we have, I'm sorry. We have done the chemistry. It's just nucleophilic addition onto the ketone. and then a quench step. So we should be able to come up with these quite quickly. And then the NMR spectrum of the final product is up to you. But it's usually something quite straightforward. It's usually, okay, I'm going to see a singlet for that. I'm going to see a septet for the CH3 group. So, sorry, you'll see a doublet for the CH3 groups. You'll see a septet for the CH group. You'll see triplet for here, singlet for here. It won't contain doublets of bananas. It really won't. It'll be fairly simple with doublets and triplets and quartets and septets, signals that you've seen before. But if you can't do that part of the molecule, that part of the problem, you can't do that. So that's the type of question that you ought to be comfortable with and start to get used to. And then in the other direction, here's a spectrum. What is the molecule? So how do we do that? I mean, this is now getting quite tricky. Once you know the basics, you've got to apply it from different directions. In this example, it's an attempt by the text to actually look at symmetry, to think about how symmetry helps you work out structure. And we have a couple of chapters of benzene chemistry coming up pretty quickly here, so we'll be able to see exactly how this applies before the next exam. But we can start in this type of picture by looking at symmetry. This is something you should get quickly. You should see quickly and be able to come up with arguments as to why this is the case and then use it. So I've got a molecule here which is symmetrical through the middle. Yeah, left matches right, and I can fold it in half and it's the same thing. So I have obviously the two types of benzyl protons. They're equivalent, so you just need one signal. And then down here we've got blue, and they're equivalent because they're the same across that symmetry line, and then those two down there. So that's 3. Now look at the next one. We change this from a 1,2. I might as well get this out of the way now and just put this in. A 1,2 substituted benzene is also referred to as ortho. O-R-T-H-O. It's coming up very quickly here when we get back into the mechanism, so we might as well see it now. Ortho protons, 1,2. And if you move to the 1,3 pattern, you're going to talk about meta. M-E-T-A. That's a meta situation. Pharmaceutical chemistry is just full of benzene derivatives, so we need to be comfortable with this. Now, that meta derivative has a different set of signals and a different number of signals because the symmetry's changed, and now I have this species right here, this thing, which is unique. It's between the two methyls where the other protons are not. So I can see the methyls here, definitely one type, that's 2 at the top. These are equivalent, 3, and the bottom 4. You need to do this quickly. Now, this one at the far right, why only 2 signals? That's really helpful, but also really a pain when you're trying to work things out. Why only 2 signals? It's symmetrical this way, and where else? Across. It's symmetrical across. So the methyl groups are equivalent, as they have been in the other molecules. And this hydrogen is the same as this one through symmetry, but it's also the same as that one through symmetry. So you only see 2 signals. And that can be helpful or not, depending upon how much work you've done. So we start to think about how we use this. We'll start to think about a process to be able to put together, to be able to solve problems. What I want to do is just start thinking about how this works and then do some C13. And then through Monday, I'll be done with NMR and then back into mechanism, which everybody wants to do. But there is a process. You're given a spectrum and you're given a formula, and your job is to work out what the molecule is. That's difficult. So we might have a formula from which we can calculate the degrees of unsaturation, the hydrogen deficiency index. And that formula will always be on the test if you need it, right? You won't need to have to worry about that. You'll then look at the spectrum and start to think about where things are, how many signals there are, what shapes they are, what the integrations are, and somehow work out from there the structure. So first off, the obvious thing is to count the number of signals. If you've got 6 signals, you've got 6 types of proton. Then you start thinking about integration, because that tells you how many of each you have. Yeah, it's a ratio again, so be careful, but it does tell you how many of each of the types of protons you have. And then here's the hard part. Building fragments. It's a bit like synthesis, a bit like retrosynthesis. You probably can't look at a spectrum and tell me straight off what it is. Very few people can do that. I'm not sure I can do that. But you can draw fragments down, you can scribble down pieces. And this will be where you pick up points, you know, this idea of getting partial credit as you work your way through. Draw the fragments. If you recognize an isopropyl group, write it down. If you recognize a benzene ring, write it down. At the end of the day, you might get 7 out of 10, even if you didn't get the right answer, because you wrote it down and you were starting to do the process in a systematic, logical way. So down at the bottom, you'll see fragments. You'll see clues. You know, here's a 5 hydrogen multiplet down at 7 maybe for a benzene ring. Here's 2 hydrogen triplets further up the spectrum. And then you put it all together, and here, this will be from the proton spectrum at 9. You can start to come out with the answer. You don't always get the right answer, but you might get close. Now, let me point out one thing since I have this molecule on the slide. What shape is that signal? If you're not sure it's an aldehyde from the NMR spectrum, where else would you go to look to see if it is an aldehyde? The IR spectrum, right? So you've always got enough information, and I spend a lot of time writing these questions to make sure that they fit within the parameters you're given, and that we're not sitting there trying to solve a problem that's impossible to do. So you've always got enough information to do this. The problem is a lot of information can be intimidating, it can be scary, and it can mean nothing if you're not ready for it. So I'm going to change pace for a little bit. This doesn't take long. I'll do this 20 minutes now. I'll do it for 25 minutes on Monday, and then we're done with NMR spectroscopy. So, you know, young Hohmann at the back up there was talking about the idea of which nuclei spin and which nuclei respond here and which don't. It tends to be things that have an odd number of protons. So C13, yes. C12, no. Proton, yes. Deuterium, no. Now, there's a problem here, just a logistical problem. When we deal with H1 versus D2, most of hydrogen is H1. That means that all the molecules will have an abundance of H1, and the spectrum is really easy to collect. The problem with C13, or carbon NMR, is that, as it says on this second line, C12 is not active here, C13 is. And the problem is, for any sample, C13 is only present in less than 1%. What that means as a chemist trying to run these spectra is that you need either more sample to be able to detect this stuff, or you need to run the sample for longer. So if you do spectra in the future, you'll do a proton in about 5 minutes. A C13 spectrum could take you overnight or a week. For a biological sample, if you don't have much of it, maybe a month. Right? These are very, very long experiments. So it is the same technique. We do see C13 and not C12. The scale is going to change. We'll talk about something called decoupled and coupled in a second to simplify these things. You do get splitting in C13, which can be a help or not. The number of signals, again, like it did for proton, it told you the number of types of proton. Here it will tell you the number of types of carbon. You put the two together, very powerful. Same ideas. Electron withdrawing groups will de-shield. Benzene carbons tend to be further downfield than alkyl carbons. Same ideas from proton, nothing too tricky there. We still do the spectra in a deuterated solvent, CDCl3, and I'll point out that that can be a confusing thing because there will be a 3-line signal exactly at 77 for the carbon in CDCl3. It's not part of your molecule. If you see that in the book, you see it on problems online, it's not part of your molecule, it's a solvent. So don't get confused by that. But the experiment's the same. Pop it in the instrument, run it for a few hours maybe, and you get a carbon-13 spectrum. What we have here, just to get started, is a comparison between two. One is a proton at the top, and at the bottom we have a C13 spectrum. Now, this proton spectrum, we all talked about shapes. There's a triplet, there's a triplet, there's a multiplet maybe, there's a multiplet. We know this stuff. And everything's to the right-hand side of the spectrum because there's only one electron withdrawing group in there. So we can certainly say that the blue hydrogens here are here because they're chlorine neighbor. Now at the bottom we have the C13 spectrum for the same molecule. Down here, that's what I just mentioned. 77, ignore it. That's the solvent. It's not part of your molecule. But we do see signals. And if this is 1, 2, 3, 4, 5, it's 1 chloropentane, then we expect to see 5 carbons in the C13 spectrum. You can see here 1, 2, 3, 4, 5. Now which of those is the closest to chlorine? The one furthest downfield, the one at about 40, 45. Those numbers are on your chart. So now you can start to use all of that chart to be able to work out problems. You can tell without even knowing that number that it's next to something electron withdrawing because it is downfield. The same ideas apply. And these are nicely split. These are nicely spread out. You can see here it's not difficult at all to read these things. They're nicely spread out. And each of them is a singlet. And I need to explain that. In reality, when you first run this experiment, you don't see singlets. You see multiplets, or you see doublets and triplets and quartets like you would for the proton spectrum. But listen to this carefully. It's not the carbons splitting each other, it's the carbons and the hydrogens splitting. So if you have a carbon with a hydrogen on it, that hydrogen has something to say about the shape. And n+1 still applies, and this will confuse you over the weekend. In a proton spectrum, it's the neighboring protons that have a say about the shape of the signals. In a carbon spectrum, it's the number of hydrogens on that carbon that have a say about the shape of the signal. So if you have a CH2 group, it'll be a triplet. If you have a CH3 group, it'll be a quartet. Now what we've done here is we have avoided that problem. We have something called a decoupled spectrum. Decoupled. I think that says decoupled. And it's an experiment in which you get rid of the influence of the hydrogens. You don't chop them off or anything. You just saturate the sample so that they're not having any conversation with the carbons, and we get nice clean singlets. You will see both, and you'll have to be concerned about both. So here we go. This is a C13 decoupled spectrum of what is a fairly complicated unsaturated ketone. And the NMR spectrum of this, you'll be able to work out yourselves. You've got an isopropyl group, it looks like up there. You've got an alpha to carbon, carbonyl type signal. You've got some double bond protons which are trans to each other. So the coupling constant should be about 16 hertz. And that stuff we've covered. Well, this is the C13 spectrum. I need to point out the scale is different. We still start at 0, obviously, and we end up about 200, 210. We don't go much further down than 210. It's a different nucleus. You expect to see a different set of frequencies for the absorbances. And this is what we look at. You will start to see data in two forms. You'll be given the chart or the spectrum, and you'll be given this at the bottom. They are the same thing. Some people like to look at the graphs, and it's easy for them to comprehend then what the answer is or what we're looking at. Some people prefer the linear data to get exact numbers. Both of them will be presented, so you've got them in front of you. Well, let's think about this thing up here. We go all the way down to 200. I'm trying to point out typical types of signal where they show. What about the, what is this up here? What's the big signal up there? Two methyl groups. Now let me say this carefully. You don't integrate C13 spectra. The C13 integration is unreliable. It doesn't work as well as it does for proton. But if the signal is twice as big in a C13, it probably corresponds to two atoms. In this case, two methyl groups which are equivalent. So if the signal is 3 times as big, what type of species can you think of that has a C13 signal that is 3 times as big as everything else? T-butyl, right? Again, there are some very simple patterns that you can get used to and bring with you when you need to use them. So this certainly are the two CH3 groups. And then I'm working my way down. I've got this guy here, which is an alkyl type, and I've got this, which is alpha to carbonyl, and they're showing there. Okay? So the influence is not as dramatic maybe as it might be for the proton spectrum, but they certainly are further downfield than the simple alkyl groups. Now, working our way down. What are these two here? 2 carbons on the alkene. Again, we're going to see some matches and some sort of commonalities here where if you look at the NMR spectrum, the proton spectrum, the signals for those 2 protons on the double bond are around 5, halfway down the spectrum, 2/3 of the way down the spectrum. In this case, they're around about 130, 150. Right there and right there. It's the carbons now, not the protons. But they have shifted significantly. The problem with this spectrum is there is one signal that would not show on a proton spectrum. The carbonyl, right here. There is no proton there. So it's not going to show. So that carbon now seems to be all the way down here. It's about 200. You look on your chart, ketones and aldehyde carbons all the way down at 200, a dead giveaway. Ester carbons, 175, a dead giveaway. They're always there in the same place. Why is that carbonyl carbon so far downfield? It is incredibly deshielded, but what phenomenon makes it deshielded? That carbon is as far downfield as we can go. We're going to come back to this when we do some more mechanisms on carbonyls, but that resonance structure is incredibly important. That explains its chemistry. It is a very, very, very polar pi bond. And so if you think about deshielding being electron density being pulled away, that picture there is about as extreme as it gets. It looks like a carbocation. It looks like a resonance stabilized carbocation. So that is very, very deshielded and therefore sent all the way downfield to the left. The way you do this is practice, and if you can do proton, you can do carbon. This is much more straightforward than proton. Okay? So I've shown you a little bit about intensity of signals. I've shown you a little bit about chemical shift. We don't spend all the time on this because we've already done the proton. These two are a comparison of that molecule's proton spectrum with its carbon spectrum. You're going to get both. And most of the questions you need to deal with, you're going to get both. So at the top, I've got a doublet, because that's for these methyl groups, which have one neighbor. They are alkyl groups, so therefore to the far right. Look how that corresponds up here. That signal for the carbons of those methyl groups is still to the far right. Not deshielded very much. Then we move down. What signal is this? It's a 3-hydrogen singlet. What is that? It's next to the ketone. Alpha to carbonyl. And what about the little one down here? I'll tell you it's a septet. I think, oh no, actually it's more complicated than that. It's actually an octet. That one right there has 6 neighbors here and 1 neighbor there. So they're extra splitting. And that right there, they are both alkyl, but they've got something next door that deshields them. Maybe this one is a allylic. See, that one's a allylic. This one is alpha carbonyl. They've been dragged downfield. Now in the C13 spectrum, it's not as dramatic, but they still are further downfield than the methyl groups. It's still consistent. All the way down here, those two are for the alkene protons, and you can see again that they correspond roughly to where the carbon show in the C13 spectrum. So it is consistent. The only one that doesn't show in the proton spectrum is down there because there's no proton on that carbonyl carbon. Now, this becomes very useful if you're on top of it to be able to solve problems quickly. And that can be a problem on the next test. We have 2 samples. One of these things is a poison, one of these things isn't. And you've got to drink the right one. Of course. So you take out your NMR spectrometer, and you take a sample and you measure the spectra of each of them, and you try to work out which is which. And on the left I have the good molecule, let's say. On the right I have the bad molecule. Which is which? Which spectrum belongs to which molecule? So let's think about what's happening here. It's all about how many signals. In this case, it isn't really about where the signals are, right? They're isomers of each other, so they have very similar chemical shifts. It's all about maybe the number of signals and maybe the intensity of the signals. So what is this molecule on the left that this molecule on the right is not? Does everybody see symmetry? It is. Huba, you see symmetry? Good man. It is symmetrical. And somebody will ask me, well, isn't this carbonyl to the left and this methyl to the right? And I will say no, because that's spinning and you can't see it. The NMR spectrometer can't see it, right? It's spinning so quickly that it just sees this sort of propeller, this cone of electron density. So this thing is symmetrical. That will cause you to have fewer signals than this molecule over here. So let's count, right? 1, the same as that. 2 is different. 3, 4, 5, 6, 7, 8 signals, I think. Anybody disagree? I think 8 signals. What about this over here? 1 is the same as that. 2, 3, 4, 5, 6, 7, 8, 9, 10 signals. There should be more signals. So make a note of this. Symmetry simplifies the C13 spectrum. That was alliteration, wasn't it? Almost. Symmetry simplifies C13 spectrum. If you have a simpler spectrum, it's probably got some symmetry in there. So let's get rid of the noise. Is this molecule the top spectrum or the bottom spectrum? Top. Who thinks the top? Everybody. Wrong. No, correct. Right? It's the top spectrum. How do we know? Because we have fewer signals. Now, there's also some help here because that benzene ring over there doesn't have any symmetry. You see all 6 carbons. All 6 carbons means 6 signals down there. Maybe, I see 5, maybe 2 of them on top of each other. But I see up here only 4 signals. And keep in mind where we are about to go with the benzene chemistry. We're about to make benzene derivatives and then analyze them and work out what happened in terms of their substitution patterns. So now I can see, well, I've got a proton here, that's 1 of them, a proton there, that's 2 of them. Why do I have 2 signals taller than the other 2? These are all for the benzene. Why are 2 larger? 2 sets of them are the same. This carbon is the same as this one, and this one is the same as this one. So you expect 2 signals that are larger, and then the top one and the bottom one are different, and only 1 of each of them, so therefore smaller. It's that simple.